Okay, welcome to the 3-4 notes for Calculus 1. You had an intro to several of the differentiation rules in the prior section. In reality, you probably could only, compute, let's say, 15% of all derivatives with the rules that you found. Why? Because most derivatives are more involved than what you actually saw. So over the next several sections, we're going to be covering specialty derivative formulas for two types of scenarios. One, for specific types of functions, like for example, you will be doing trigonometry derivatives soon. But you also, in this section, for example, need to conquer rules that are more about situations that you run into than anything else. That's going to be the key for where we're going with this. Okay, so just as here, it says, in the prior section, we discussed that the derivative of a sum or difference is equivalent to the sum or difference of the respective derivatives. For example, this. So if we have the sum of two functions, or the difference, we'll just do sum for now, then that's the equivalent of basically distributing the derivative concept to both, taking the derivative of them and just adding them together, or could be subtracting, okay? But what if we go to the other two operations? What if we went to products or quotients? Well, we're going to start with products, or in other words, multiplication. So what are we trying to prove, essentially? If we took the derivative of the product of two functions, right here, would that be equivalent to the product of their individual derivatives? That is the question we must answer. In order to determine that, I brought in a very unique situation. So what I did basically was I provided a function f, which is x cubed, and a function g, which is x to the fourth. In order to prove this scenario right here, whether these two sides are actually the same, what we're going to do is we're going to find each piece of this using these two functions and then determine if they are the same. That is our goal. So let's start. For example, let's start on the left side. Let's say we're taking the derivative of the product of these two quantities. So let's say that they are together. In other words, we want to find the derivative of literally x cubed times x to the fourth. Well, we know that we can multiply those two things and get x to the, well, when we multiply two powers that have the same base, we can add their exponents and get x to the seventh. Well, we know the derivative of x to the seventh, and hopefully you're experts at this by now, is going to be 7x to the sixth. So the derivative, the left side of this, is going to be 7x to the sixth. Now let's see if the right side of this is the same. If it is, then we can distribute the derivative and use this rule. If it isn't, that means we have a problem, and then this is the improper way to do this problem. So let's look at f prime of x times g prime of x. Well, f prime of x is the derivative of x cubed, right? And what we need to do is multiply the derivative of g, which is x to the fourth. So this is different. We have to take the derivative beforehand. So if we want to find this is 3x squared. If we want to find this, it's going to be 4x cubed. And if we multiply them, we get 12x to the fifth. So look at this and look at this. These are clearly not the same. Therefore, we know for sure that this does not work. So in order to find the product, the derivative of a product, we cannot just find the derivative of each function and then multiply them. It's not the same as our original sum and differences, which means we need a special rule in order to accomplish that. What is the special rule? It's called the product rule. Okay, so jumping into it. So the product rule is essentially this. If you take the derivative of a product, it is equivalent to the derivative of f times the original function g plus the original function f times the derivative of g. This is a formula that you will need to memorize and know very well because when you go through problems, you will not have mental time to keep going back and forth to look at the formula. It really is a waste of time to do, especially with how complex these are going to be. So the goal right away is, just like in the previous section, memorize this formula. Very easy to do, and it'll be very beneficial for you to do that. So last time we tried to use in the standpoint the derivative of the functions right here, which is this. So this is the true answer to the problem, by the way, because we did it out like this, but we tried to use this in order to accomplish it. This was not correct. So this is not correct. So let's use the product rule and see if we can actually get the correct result. So here we go. Derivative of our product. So in this case, our derivative of our product, x cubed times x to the fourth, is equal to, according to this formula, first we find the derivative of f. So the derivative of x cubed. Then we multiply by the original function g. So that's just x to the fourth. Okay, then we add the original function f, which is x cubed, times the derivative of g, which is x to the fourth. Okay, what you're going to have to get used to in these problems is you're going to be creating derivatives in the course of trying to find derivatives, if that makes any sense. So like here, we have a single derivative of this product, but we're going to be creating derivatives trying to do that. So before we can even ever finish the problem, we have to find the derivatives, all the derivatives first, then combine the function. So what's the derivative of x cubed? 3x squared. We bring the x to the fourth with it, plus x cubed, which is there, doesn't change, times the derivative of x to the fourth, which is 4x cubed. If we multiply these out now that the ddx's are gone and the derivatives are found, we get 3x to the sixth plus 4x to the sixth, and if we add those, we get 7x to the sixth. So as you can clearly see here, we get the proper answer to this problem, and the derivative of x cubed times x to the fourth, the product, is going to be 7x to the sixth. Okay, so the way I'm going to teach you this is this product rule using examples is very similar to what we did in the mini example here in the sort of the proof. So I'm stating that the derivatives are going to get extremely complex. So in order to make sure that you're always on task in terms of not making a mistake anywhere by taking shortcuts, I'm very, very serious about making sure that you follow exactly what I'm doing, even if it seems like it's maybe a little bit too anal, I guess is the best way to put it. A little bit more too detailed, because soon the detail is going to save you. Okay, that's the best way for me to put it. So what do I mean by that? Look at number one. So the y is equal to 2x cubed times 4x squared minus 5. So right now we technically have the ability to distribute both of these right here. I'm not going to do that. I'm just going to show you how the product rule is actually used, because I think it's the best thing to do here in terms of doing this, making sure you understand that this is clearly a product. So look at our setup on the left side here. It looks like this is going to be f, and this is going to be g. So in order to find the derivative of the product, we want to use essentially the product rule. Okay, so there's a couple ways we could write the derivative on the left side. So we could write y prime. That's one shortcut to writing the derivative. But more commonly, you see dy dx. Okay, so the derivative of y is dy dx. So dy dx is going to be equal to what? Well, first we have to take the derivative of f. Well, the derivative of f is d dx of 2x cubed. Now, some of you are going to want to just do the mental math right in the beginning. This is what I mean by being anal. I would not suggest that. I'm fine with you doing it in earlier derivatives, but once we get to these rules, and I'll explain why in a second, I would do this out in detail. So next we need to multiply by just g, which is 4x squared minus 5. We need to add. We're going to the function f, which is 2x cubed, and then multiplying by the derivative of g, which you want to write out as this. Okay, so again, there's a very good chance that some of you might have looked at the derivative of each one of these and just did it. While this would work, it turns out that later on, when you go to find this derivative, it might not be simple. It might not just, so many of you are looking at this and going, well, duh, professor, we already know that this is going to be just 6x. Well, true. So let's just do it for a sec. So this, if you put the 3 over here, we're going to get 6x squared as our derivative. Over here, we bring this down because there's no derivative sign. Here, we bring this down. And then we multiply by the derivative of this, which is going to be 2 to the front, 8x minus 0, which is 8x. So this is pretty simple. I'm not going to lie. Like, you could have taken a shortcut and it wouldn't have hurt you. But what's going to happen is later on, these derivatives are going to be extremely complicated. And some students, by taking shortcuts, completely miss that. So what I would say is when you're doing these problems, always write it out exactly the way I'm writing it out. I always tell students, I'm always very lenient with little shortcut things that aren't going to hurt you. This, it could hurt your grade if you don't take these very simple steps. So the rest of this is just combining everything. So distributive property gets you 24x to the fourth minus 30x squared. Over here, if we multiply, we get 16x to the fourth. If we combine these, we end up with, it looks like 40x to the fourth minus 30x squared. So this is the derivative of this function. Okay, so again, I want to be very clear. Even though we're in a different rule, we have not abandoned the same concept as before. If we graph this function, we find and we want to determine what the slope of the tangent line is at any point, it's going to be this function over here. Okay, before we move on, I want to be very clear with you that this problem could have been done without the product rule. And you have the freedom to do so unless the problem tells you that. I like doing it because I want to prove it to you. So right now I'm going to prove to you that this product rule works. And how do you do that? Well, let's first distribute our original function. So our original function would be y equals 8x to the fifth minus 10x cubed. So if we find dy dx without the product rule, we just have to do it directly. So 5 goes to the front, we get 40. It leaves the exponent 4. 3 goes to the front, get 30. Leave the exponent 2. And hey, look at this. That was quick. So yeah, way easier to use the distributive property and do basic derivatives. But that isn't allowed a lot of the time with the problem you're going to do, which I'm going to show you here in a sec. But I wanted to show you that you could have done this differently in this context if you wanted to. So if it hadn't said, use the product rule, then you could have just distributed and you've done the basic rules. All right, so let's look at number 2. So let's say we had y equals x squared 2 to the x. So clearly, if you look at these, we have two different functions, x squared and 2 to the x. You just learned in the previous section that the first function is a power function and the second one is an exponential. They cannot be combined. They do not have the same base. They're completely separate functions. So what do? We treat them as f and g, and we're taking the product of that. So what do we need in order to do the problem? We need I already gave that away. We need the product rule, right? So let's do that. So dy dx is going to be equal to, again, we're going to do the derivative of f, so that's d dx of x squared, times the original function g, 2 to the x, plus the original function f, which is x squared, times d dx of g, which is 2 to the x. Okay, note I was very, very detailed in how I wrote this. I left the original functions as they were, and I put d dx's in front of the other ones. So now I know I have to find the derivative of this, which is 2x. I now can bring the 2 to the x along for the ride. The x squared comes down again, and then the derivative of 2 to the x, well, let's see how much you remember. So right now, think about it, okay? What is the derivative of b to the x? It is b to the x natural log of b. There's your result that you get. So, in a sense, if you look at any of these quantities in this scenario, there's nothing that actually can be combined. So technically, the answer is 2x 2 to the x plus x squared 2 to the x natural log of 2. So no different than what you see up here, right? The thing is that a lot of times in mathematicians look at this and see how ugly it is and how misleading it looks, because we got 2x and 2 to the x, it just looks bad. So what you'll find sometimes in, let's say, the answer key in the book, or sometimes in my math lab, is that they will represent it in a different way. So I'm just going to write alt, or alternate answer. Okay, I will accept either, but I want you, just in case my math lab asks you for it, just take out a GCF. So if you look at these quantities, what GCF do they have? Well, they both have an x. They both have a 2 to the x. So if we take that out, we're going to get 2 plus an x natural log of 2 left over. So sometimes the answer is written like this, sometimes it's written like that. I just want to be clear with you that either one exists. Now, before I leave the problem, I want to be clear that you could not have found this derivative with anything else but the product rule. There's no way to do it, which means the product rule is essential to doing many of the derivative problems we're going to do. Again, I highly recommend, even if this is clearly an online class, I get it, but when it comes to exams and going through and understanding this well, you just have to memorize this rule so that you don't have to keep looking back and wasting time doing that. And you're going to be memorizing a lot, I know, but it's in the best interest for you to do so. Similar to products, quotients also don't follow the very easy sum and difference rule that we had before. So if you take the derivative of a quotient, that will not be the quotient of their derivative. So basically it's not equal to f prime of x over g prime of x. It's not a valid rule that actually works. So don't try to do it, because you'll be, the students who really bomb in the class are the ones who just don't understand and end up just taking these simple derivatives that break all the rules. You can't do it. So instead, what we have is we have a formula that we call the quotient rule. Now, the quotient rule does look pretty complicated, but I do share something with students that will make it a little bit easier. So what I have them do is I basically have them reverse these two variables right here, right? Instead of g of x f prime of x, I do f prime of x g of x. It's exactly the same thing mathematically, but why do I do that? Well, if you look back at the product rule is exactly the same except with a minus sign in the numerator. So basically the numerator of this thing is the product rule with a minus sign. So it makes life a little bit easier for you in terms of memorization. So all you have to remember is, okay, the quotient rule is the difference product rule divided by the original function g squared. If you can memorize that, then you'll be in good shape and you'll understand. You won't have to go back and keep on looking at the formulas, which is no good in calculus. Okay, so let's look at number 3 here. So clearly we have a quotient, right? And we need to take the derivative of that quotient, dy dx. So what you don't do? Let's do that real quick. So what you don't do is you don't find the derivative of the numerator and the derivative of the denominator and say that's the derivative. Again, that's convulsion territory for your professor. No kidding. On an exam, I might, if I'm grading an exam. Do not do that. This is strictly called the quotient rule, and you must apply it. Again, just like the product rule, write it out. Write it out. So how do you do that? So first things first. the derivative is going to be, the numerator is going to start with the derivative of f. Well, in a quotient, f is going to be the numerator and g is going to be the denominator. So the derivative of f, x squared plus 3x, times the original function g, which is 2x minus 1, minus, so remember it's a minus, the original function f, which is x squared plus 3x, times the derivative of 2x minus 1. That is going to be all over the original function g, 2x minus 1 squared. The biggest mistake students make is they get everything in the numerator right and they forget to write the denominator altogether. Obviously, don't do that. That would be bad. Okay, so what do you want to do? So I actually give students a little bit of a break when it comes to the quotient rule. As you see, this thing is an absolute beast. It's a huge derivative, right? So what I don't want to do in this class is I don't want you to spend a numerous amount of time doing algebra, like all types of things involved with that. If you're in calculus, you better know how to do algebra. So I actually give a little bit of a shortcut. So what I do for students is I have them do sort of patchwork. So find the derivatives individually within the problem. So the derivative of x squared plus 3x is 2x plus 3. The derivative of 2x minus 1 is 2. So all you have to do next is write it out. So 2x plus 3 times 2x minus 1 minus this 2, clearly, we wouldn't write x squared plus 3x times 2. We would write 2 times x squared plus 3x. All over 2x minus 1, quantity squared. So I am okay with you just circling or boxing that as your answer. Okay, you do not need to keep on going because what do? The numerator, you're going to FOIL over on the left over here, right? And then you're going to distribute the negative 2, and then you're going to collect like terms. You're going to square the denominator. It's an extra minute or something that it's just not important. If you're giving me this, then I know you understand the calculus, which is what I'm looking for. You understand the quotient rule, and that's what I want to be very clear with. Something that I see real quick that I want to make sure you don't do. You guys see this? Okay. You cannot simplify those two things. I know I said you don't need to simplify, but some students do it anyway, and then you do it wrong. You cannot simplify that because there's no 2x minus 1 on the right side. So just make sure that you don't make those types of mistakes by doing things that are algebraically not sound with what you're doing. So literally, this is your answer to the problem. This right here. Okay, so let's try another one. So we got y equals 1,000 over 10 plus 3x, 3 to e to the x. So we're going to get dy dx. Clearly, this is a quotient where the numerator is f and the denominator is g. So if we follow the letter of the law, what are we going to get? We're going to get derivative of our f function, which is 1,000, times our original function, 10 plus 3 e to the x, minus, don't forget the minus, our original function numerator, which is 1,000, times the derivative of 10 plus 3e to the x, all over our g, 10 plus 3e to the x squared. All right, so where do we go from there? Again, you can take this shortcut. Let me get rid of this. You can take this shortcut. I'm perfectly fine with it. So what do you get? So for derivative of 1,000, you get 0. Okay, so what beautiful thing then happens with this entire thing in our numerator becomes 0. That's fantastic. On the right side, what's the derivative of 10 plus 3e to the x? Well, the derivative of 10 is 0. The derivative of 3e to the x is, well, the constant multiple stays. And the derivative of e to the x is e to the x. So we basically just get 3e to the x as our derivative. So all we have to do is write that out as a result. So once again, we get 0 over here. So it's going to be 0 minus 1,000 times 3e to the x all over 10 plus 3e to the x squared. And we can simplify that a little bit. It looks like it's going to be, so be careful here. So the 0 goes away, but this negative is still here. So we're going to get negative 3,000 e to the x over 10 plus 3 e to the x squared. And this is the derivative of your original function. It is imperative that on your homework, and if you need more because the homework isn't enough, the lab and the homeworks, that you practice this like crazy. If you expect to get this by just doing a couple problems and then, hey, we'll give it a shot on the exam, don't even try. So just make sure that you practice this like crazy when you're doing the problems. All right. So you might recall that in the previous section, you learned that the derivative of e to the x is itself. Okay? We proved that using the b to the x formula. So there's actually a very interesting development that happens. What if we have a constant with the x in the numerator? For example, what if we had e to the 2x? Well, it turns out that if we have e to the kx, like this, the derivative is always going to be ke to the kx. So the derivative of this would end up being 2e to the 2x. This is a fact. This is a very mini formula that for now you can memorize. You will learn a formula later, or a rule called the chain rule, that will show you why this actually happens. This textbook wants to use e early on, so they throw in this shortcut formula to help you out. So let's look at what a problem would look like. So we have a function, f of x, which is equal to 1,000 e to the 3x. So again, what does this look like? It looks like a constant and a function, right? So what do we know when we find the derivative f prime of x? Well, we know that the 100, the constant, stays put, and we multiply by the derivative of the f of x, which is that. Well, what do we now know? The derivative of e to the kx is ke to the kx. And when we multiply, we get 300e to the 3x as our derivative. Okay, so I want to touch on something. Before I get to page 34, which is going to be like taking all the stuff and shoving in the same problem, creating crazy problems. Before I do that, I just want to talk about terminology. So if in this problem you see that I had a function, f of x, and I used f prime of x. So you might have noticed in the previous part here I did y and dy dx. Just so you know, this is basically the same thing. So I have an original equation, and I want to find its derivative. I have an original equation, I want to find its derivative. It's just a different way to write the same thing. But just so you understand why I did that specifically with these problems, well, the formula uses f and g. So I didn't want to write f of x right here because we're treating the top as f and the bottom as g. I thought that might be really confusing for students. So normally when I do quotient rule problems or product rule problems, I usually put a y. Even though it is a function, I put a y on the left side just so you don't get confused with the f of x and the g of x's. Okay, the other part of this, I want you to take a close look at this function right here. So many students, when they see this, they go, all right, Professor, and I've gotten this question in class, so I'm just going to act it out like a play. I get the question, so Professor, why is it you didn't use the product rule for this problem? Because, hey, that's logical. I have a product going on here. I have a function, which technically could be 100, and I have another function, which technically could be e to the 3x. So why didn't you use the product rule? All right, well, let's take a peek at it. So pretend this is y. So what would be this as a product rule? Well, it would be d dx of 100 times the original function e to the 3x plus the original function 100 times the derivative of e to the 3x. All right, well, derivative of this is 0. Derivative of this is 3e to the 3x. What happens? This wipes out, and we get 300 e to the 3x. Hey, look at this. Fantastic. You get the same answer. So the answer is, yeah, you could have used the product rule. But why on earth would you use the product rule and go through all of this craziness when this is so easy. So easy. So what I say is to students, if you have a product where one of the elements is a constant, don't use the product rule. Just use a constant multiple like c and f of x. And then find the derivative by leaving c and then multiplying by the derivative f prime of x. So part of your journey in this class is deciphering between what you get. Because on the exam, it's not going to say, use the product rule, use the power rule, use the quotient rule. You're going to just get a total disarray of functions, and you have to find the derivatives and find what you need to do. You're not going to be told to do that, most likely. So that's part of the process of the class, is looking at a problem and knowing which rule you need to use, which, by the way, is a great segue for this last page. It says, let's do some more practice of these two very important derivative rules. Be aware there are also some scenarios where you will have to utilize both the product and quotient rule in the same derivative calculation. Okay, so that's to come. But let's talk about some of the crazy derivatives that you're going to end up having to take. And again, we're not even close to the insano steroid-infested derivatives that you're going to see yet. And you're going to be floored by that statement once you see what we're going to do in a second. But trust me, you're not even close. So again, take this all with a grain of salt and learn it skill level at a time and try to absorb everything. So look at our first function here, 6. So we have y equals the 4th root of x plus xe to the 5x. So your goal in this problem is to locate things that are familiar to you. For example, when I look at the 4th root of x, I immediately look at that and go, hey, 2 sections ago, or 1 section ago, it feels like 2, but a section ago, I learned that I don't have a rule for radicals when it comes to derivatives. So I need to turn any radical into a fractional exponent. Okay? So we're going to rewrite this function like this. When we're there, we can finally find the derivative. Well, look what we have here. If we want to find the derivative of this function, dy dx, there's a plus sign, which means I can find the derivative of each piece of our formula. So I purposely threw this one in here, so you remember that although this does not work for products and quotients, it works just fine for distributing the derivative to sums or differences. So right now we have this. So you have to write the ddx's. Why? Because you could have taken, if you just tried to do this mentally and this mentally right now, you would have missed out on a very important concept going on right here. What is this? What are you looking at right now? Well, I'm looking at an x and an e5 to the x that have nothing to do with each other. They're actually two different functions, f and g, that have a multiplication symbol between them. Not literally, but it's not there, but it's there. Which means, what rule do I need to find this actual derivative? I need the product rule. So here we go. The first part of this is just a straight derivative. So let's do the math. If it's a power, the 4th goes to the front, the x comes down, and we need to subtract 1 from the derivative. So we'll take care of that math later. 4, and I'm going to put a bracket here so it separates the problem. For the derivative of a product, I need the product rule. So remember, the product rule is essentially we don't want to do that. Yeah, we could do that. So it's going to be f prime of g times g plus g times g prime. Actually, let's do it this way. So go back to the thing. I'm going to do a shortcut version of it, right? Where are you? So I'm going to rule out the x's for this when I'm doing it. The x's here. So I'm going to do f prime g plus f g prime. Just to make it super quick. Going back, plus f g prime. Just to make life a little easier so we don't have to write out the x's. And that's fine. So what do we get? So we start with the derivative of our f, which is our x, times e to the 5x, our original g, plus basically f, which is x, times the derivative of e to the 5x. Okay, so these brackets are not needed, but worth noting, if this had been a minus sign, those brackets would definitely have been needed, because you would have had to distribute this sign here to both of the quantities on the right using the distributor property. Don't lose track of that when you're doing problems, because that will be devastating. So notice that we have some simplifying to do, right? So one is we'll do that. So here, what do we have? We have 1/4, and we have x to, it looks like 1/4 minus 1 is negative 3/4 in our problem here. Negative 3/4, and then technically that's over 1. We have the derivative of x, which is 1, so it's a 1x. Anything times x, you get that derivative. E to the 5x plus x times the derivative of e to the 5x. Well, what is that? That's 5e to the 5x. If for some reason, you don't need that last bracket. Notice that I removed the brackets because I'm not distributing. I could leave them if I wanted to. Okay, so more simplifying. So here we have 1 over x to the 3/4 goes to the denominator, and we get 4x to the positive 3/4. You should be very good at that by now if you're doing the homework. Here we get e to the 5x. And then finally, normally we don't write x5 e to the 5x. The x makes sense being in here. So it's 5x e to the 5x. So this looks pretty good, other than maybe deciding to do 1 over 4 fourth root of x cubed plus e to the 5x plus 5x e to the 5x. Okay, but this is the derivative of your original function. So this is a crazy-ass derivative. No other way really to explain it. But again, we're not even touching the surface. So you're going to see the next two problems and you're going to be blown away. So in these problems, what's going on? You're basically, the key is looking at the original problem, the original equation, and deciphering what you see. It's not that easy, going to be honest, in the beginning here. Maybe it will be for some, but for many it's not, and it's about seeing what you see and then interpreting it from there. Okay, so let's get into the real doozies here. So 7 and 8 are actually sort of a combo deal, because they are problems that involve both the quotient and product rules together. But what students have trouble with is deciphering when to use what first. So I am going to help you with that along the way here. So just to be clear, we need to find the derivative of this function. So we need to find dy dx. So technically, that means we need to find the derivative of this entire quantity. Okay, we'll start out with a very simple step, that ddx of this quantity. So my question is, and this is the easiest way to remember, when you see this, what do you see? Well, you look, and clearly we have division, so there's a quotient, but if you look in the numerator, what do you see? You see a product. Technically, we could have distributed, but again, just for argument's sake, we're going to leave them separate so you understand how to do a problem like this. There is a product. So what do students ask me right away? Do I do the product or the quotient first? That's the first question. And usually I ask the students when I'm doing this in class, and I will get half the students raise their hand for product and half for quotient. Well, believe it or not, there's only one right answer. Okay, so how do we know? So the question I asked immediately is, in this problem, are we taking the derivative of a product or a quotient in the beginning? So in other words, we're taking the derivative of this entire quantity. What is this entire quantity? Is it a product or is it a quotient? Well, clearly the entire thing is division or a quotient, which means you must start with the quotient rule or everything will go very wrong. So how do we do that? So if you look at this really quick, this is a quotient, so we're going to treat the numerator as f and the denominator as g. So here we go. So remember the formula. So the formula is, remember, similar to this. It's f prime g, but we subtract fg prime. and it's over g squared. That is our formula. So that's what we're going to follow. So here we go. So first things first, we need to find the derivative of our entire numerator, which is x squared times 2x plus 1. Then we have to multiply by g, which is x minus 3. Subtraction, our original f, which is again x squared times 2x plus 1, times the derivative of our g, x minus 3, all over x minus 3 quantity squared. So that is a monster-looking problem, right? Monster. So let me just get rid of this so that we can do a little work here. So we have everything we need, but here's the issue. So I'm going to go over here first, and this is where, again, it allows you to do a little bit of shortcut work. So if you go over to this clearly, the derivative of x minus 3 is kind of easy. The derivative of x is 1, and the derivative of 3 is 0, so this whole thing is just 1, which means this has no effect on this guy, so we're just going to get x squared times 2x plus 1 over there. But on the left side, what is happening, folks? What is happening? What's the derivative of, we have another f and g here, which means we need the product rule in order to do this. So yes, we have to do the entire product rule within the quotient rule. So here we go. So in the numerator, so let me do the line, let me do the line here. So numerator, I'm going to do a bracket to separate the product rule. So we have to do derivative of x squared times our original function 2x plus 1 plus x squared times the derivative of 2x plus 1. So yes, I just did the entire product rule, f prime g plus, again, similar right here, fg prime. So I did that entire thing. That's in just this right here. Times, we bring down the x minus 3, and we know this is 1 already, so we're just doing x squared times 2x plus 1 over on the right side, all over x minus 3 squared. So can you imagine, by the way, simplifying this whole thing? I can't, so you don't have to. All you have to do is go to the point where you found all of the derivatives. So real quick, look at this. Here we have another derivative thing going on here. So what's this derivative? It's 2x. What's the derivative of 2x plus 1? It's 2. So all we have to do is write out our final step here. In brackets, it's going to be 2x times 2x plus 1 plus, this 2 is just here, 2x squared. We're going to multiply that by x minus 3 minus x squared times 2x plus 1 all over x minus 3 squared. And this is your derivative. Holy moly, right? So we could absolutely multiply the entire numerator out, collect like terms, maybe even get something that cancels out. But again, that is an algebra fest that I don't really need to see from you. You're going to do plenty of algebra in this class. We don't need to spend time doing that, because if you give me this, then you're telling me you completely know how to find the derivative, which is the calculus concept I need you to know for this class. So that's why we're going to stick with just right there as our result. And remember, I know this sounds crazy, but if we graph this thing right here, and we want to know what the slope of the tangent line is at, let's say, x equals 2, we would have to plug in 2 into this entire function and find that number, and that would be the slope. Okay, so last problem here in this section, and again, this is going to be a bit of a doozy, but remember what I told you before, this is like a tandem act right here, and there's a reason for that. So real quick, we need to find the derivative of this problem, which is d dx of 10 to the x times x minus 1 2x plus 3. Okay? All right, so remember in the beginning of this problem here, I asked you, what are we taking the derivative of? What is this entire thing? This entire thing is a quotient that happens to have a product inside of it. So we're taking the derivative of the entire quotient to start, hence why we needed the quotient rule. Now look at this one. Now we're taking the derivative of this entire thing. Well, I do see a quotient, but is the entire thing a quotient? No, the entire thing is a product, which means what do we need to use first? The product rule, f prime g plus fg prime. That is what we need to be able to do, right? So how do we do that? Again, this is f, and this entire business is g. So let's see how we do it. So we do the derivative of our first function, 10 to the x, times our original quotient, 2x plus 3, x minus 1 over 2x plus 3, plus, so remember over here, the quotient is minus, but the product is plus, our original function, 10 to the x, times the derivative of x minus 1 over 2x plus 3. Okay, this is the letter of the law, what we're doing. Now, it's the product rule. There is no denominator. It's just the product rule. It's just this. Okay, so remember, shortcut versions here. What can we do? Well, we could find the derivative of this. Remember, this is b to the x, which is going to give us b to the x natural log of b for the derivative. So this is 10 to the x natural log of 10. This is just going to come down. This is going to come down. But then, what do we need in order to do this? This is the derivative of a what? The quotient. So, we need the quotient rule. So yes, we have to do an entire quotient rule in the middle of this problem. So here we go. I'm going to rewrite this stuff. Okay, this left side is never going to change because the derivatives are taken care of. But this side is going to change, and I'm going to put a big bracket here to represent our quotient rule. So remember, the quotient rule is going to be f prime g minus fg prime over g squared. Okay, so what does that look like? So again, this is f and this is g, right? So we're going to get the derivative of x minus 1 times 2x plus 3 minus x minus 1 times the derivative of 2x plus 3 all over 2x plus 3 quantity squared. All right, so the only thing left to do is to find these derivatives right here. So again, you can shortcut the process. Derivative of x minus 1 is just 1. The derivative of 2x plus 3 is just 2. So we can just rewrite the final step, and yes, it's enormous. Enormous. So x minus 1, 2x plus 3. We can leave this 10 to the x here and then just do our final step. 1 times 2x plus 3 is just 2x plus 3. X minus 1 times 2, we usually put the 2 in the front just because we don't write this, right? I mean, that looks terrible. People are going to be like, wait, is that an exponent? Right? So don't do that. So get that, and that's over 2x plus 3 squared. And look at this. This is the derivative of this function. And again, it's going to get worse. So why is this bad? Because really, when you're done, you have no idea whether, a lot of times in math, you get an answer and you're like, that can't be right. You're not going to be able to do that in this class. Calculus can be quite a beast when it comes to that stuff. You don't know if you're right, basically. There's no way to check. Later on, there will be. When you get to a little bit at the end of Calc 1, we'll be able to do stuff to check work. But for now, this is your quotient rule, and the result, the derivative of the function that you'll work with. Again, before we leave, get a lot of practice with this. The practice is crucial in this class. If you're just trying to wing it, good luck. It's not going to happen. Most students cannot do that unless they are math insanity geniuses. Some are, but you got to get a lot of practice when doing this stuff.